Now, this illustration deals with general requirements for sizing conductors based upon two methods. We select one method that produces the largest conductor. Now, notice coming out the gate, if you see NEC 210, that's a branch circuit. If you see NEC 215, that's a feeder inside the building. If you see NEC 225, that's a feeder outside the building. If you was to see NEC 230, then you know that's service. So here we're looking at 210.19A1A through A1B. So we know this is a branch circuit that's routed from the panel over to the equipment, but it's routed through temperatures higher than 86 degrees Fahrenheit in accordance with table 310.16 at the very top that doesn't allow that. So it warns you about it. Make corrections. Now, method one would be to the left. It's the 125% rule. Now, if you had a continuous load, say maybe at 28 amps, multiply it by 125%, 35 amps. The rest of the loads that operate for less than 3 hours, or take it at 100% or with demand factors if permissible, and those we come up with 12 amps, 47 amps. So the application now of step 2, we'd go to table 310.16 and 240.4b. A 47 amp load, you could round up the 220.4b to 50 amp when using number 8 THHN copper conductor terminated at 60 or 75 degree terminals, whatever the equipment called for. And then that's the solution. A 50 amp overcurrent device, number 8 to THWN wire, I think, is listed there in that illustration. And then the note says the above calculation does not include any adjustment or correction factors. We're comparing method one at the 125% roof, a continuous load plus non-continuous load, to the correction factors in the method two. So in method two, notice some folks don't get this to start with till they really review it. All the loads are 100%. We're continuous, non-continuous, demand factors, whatever. We take 100%, we have 40 amps. But we're reviewing our section 210.19A1B, table 310.15, B as in boy 1, and we would look at 310.15C1. Now, with this thought in mind, step 2 can be applied. We're applying the derating factors. So we would take a 75 amp rated conductor routed through 106 degrees Fahrenheit. We have 4 current carrying conductors, so it'd be 75 amps from the 90 degree column for that wire size, times 80%, times 87% for adjustment and correction factors. We come up with 52 amp that we would have there. And we're following the information that is given to us in the illustration with the call-outs to each piece of equipment, service or equipment served. Now, step 3, table 310.16, method 1, step 1, 40 amps, would require a 52 amp, which is greater than 40. So we would have to use a number 6, THHN, copper conductors, and in the 90 degree C column, they are worth 75 amps to us. So a number 6 would be selected based upon number 6 copper conductors, protected at 50 amps. When I say 50 amps, a 50 amp overcurrent device, as permitted based upon step 2. Now, notice now we rounded down to 50 amps here in the method 2. Now, which is the largest conductor? The number 8 in method 1 or the number 6 in method 2? Well, naturally, the number 6 is the largest conductor, and that's the one we'd have to choose because the adjustment factors and the correction factors required a larger conductor than the 125% rule plus the non-continuous rule in step 1. And that's what this figure 14-17 is illustrating. But don't forget your notes. Note 1, all terminals are 60/75. Now, what does that mean to you? We can either cable at 60-degree terminals, or we can run conduit with wiring at 75 degrees C, or use even service entrance cable that's 75 degrees C rated. But all cables are 60 degrees C unless otherwise noted. And we find that in 334.80, 320.80, 330.80, all that's listed there for us. Now, in step note 2, the 52 amps is used based upon step 2 or method 2. And then note 3 used the larger methods of 1 and 2. And when we put all this together, that's what our figure 14-17 is illustrating for a branch circuit used in the conditions of use as you see in the illustration.